What if the emptiest place you can imagine isn't empty at all? What if, right now, as you lie here in the quiet, you're moving through an invisible ocean, one you can't see, can't touch, and rarely think about? Yet it quietly gives you mass, holds atoms together, and hums beneath every piece of reality you've ever known. And what if nothing isn't the absence of everything, but the presence of everything in its gentlest, most resting form? Tonight, we're going to drift into that hidden ocean, not with equations, not with pressure, just with a slow bedtime journey through the strange truth that modern physics keeps whispering to us. Space is not a blank stage. It may be the deepest thing there is. A fabric, a field, a quiet foundation that never fully falls silent. So, take a slow breath in and let it out gently. If your day has been heavy, you don't need to carry it any farther. You can set it down here for a while and let curiosity do the soft work of easing you towards sleep. Welcome to the Quantum Slumber, a place where quantum mysteries unwind at a calm, unhurried pace, where the universe takes the slower road, and your thoughts are allowed to settle. If you enjoy these quiet voyages into quantum reality, you're warmly invited to tap, like, subscribe, and join us again on future nights. And if you feel like it, leave a simple comment. Tell me where you're listening from or what time it is for you right now. I love reading those small signals from the world outside while we explore the hidden world beneath it. Now, get comfortable. Let your shoulders soften. Let your jaw unclench. And when you're ready, let's begin where intuition breaks, with space itself. For most of human history, it felt natural to imagine space as the simplest thing in existence, a kind of quiet nothing, an empty stage where the real drama happens, planets swinging in their orbits, apples falling from trees, light traveling from distant stars. Space, in that old picture, didn't do anything. It didn't participate. It didn't have texture or personality. It was just room. And when you look up at the night sky, it's easy to understand why that idea held on for so long. Between the bright points of starlight, there's darkness. Between one galaxy and the next, there's what seems like a limitless black sea. If you could sweep away the dust, the radiation, the drifting gas, if you could remove every atom you could possibly remove, what would be left? It's a comforting thought in a way, that beneath everything there is a clean emptiness, a silent background, a pure absence. But that comfort didn't survive the 20th century. Because the more carefully we listen to the universe, the more it seemed to whisper the opposite. Space is not a passive container. Space is not a stage. Space is something. The first great crack in the old intuition came in 1915, when Albert Einstein introduced the world to general relativity. It's hard to overstate how strange his revelation truly was. Before Einstein, gravity was usually pictured as an invisible force reaching across empty distance, Earth tugging on the moon, the sun tugging on the Earth, matter pulling on matter through a void. Einstein's insight was quieter, but far more radical. He said the tug isn't reaching across emptiness. Instead, the emptiness itself is shaped. Mass and energy don't simply sit in space. They change what space is like. They curve it. They bend it. They give it geometry. If you want an image that fits easily in the mind, imagine a stretched fabric, something like a trampoline surface. Place a heavy object near the center, and the fabric dips. Now, roll a smaller object nearby. It doesn't need a mysterious pulling force to be drawn inward. It simply follows the curved shape of the surface. In Einstein's view, gravity is not a ghostly hand pulling from afar. It's the contour of reality itself. Suddenly, space becomes active. It can be warped. It can be smooth in one region and steep in another. It can ripple with gravitational waves. It can expand as the universe evolves. It can be stretched so severely at the edge of a black hole that even light cannot climb back out. Even if you've heard these ideas before, it's worth letting them settle gently for a moment, because they're already enough to overturn an ancient assumption. If space can curve, if it can ripple, then it has properties. It has structure. It can change. The nothing we thought we lived in begins to look more like a fabric, subtle, invisible, but real. And just when that revelation was still being absorbed, another revolution arrived from the opposite end of the scale. Because while Einstein was reshaping our understanding of the very large, stars, galaxies, the expansion of the cosmos, physicists in the 1920s were discovering that the very small behaves in a way no ordinary intuition can hold. Quantum mechanics appeared like a strange, shimmering language. It said that the tiny constituents of matter, electrons, photons, atoms, do not behave like miniature billiard balls. They do not have a single, definite position and speed the way a marble does on a table. They behave like waves. Or, more precisely, they behave like clouds of probability, patterns that describe what might be found rather than what is. An electron around an atom isn't a tiny planet circling a tiny sun. It's a spread-out possibility, a sort of haze, with some places more likely than others. And that's a beautiful idea, in its own way, dreamlike, almost soft, but it carries a question that is easy to miss until you sit with it in the quiet. Waves in what? Water waves need water. Sound waves need air. A ripple needs a medium. Even a vibration in a guitar string needs the string. So, what is a quantum wave? A wave of... What is it that wiggles when an electron behaves like a wave? At first, you might think the answer is simply space. The electron wave is a wave in space. But that only pushes the mystery one step back. Because now you must ask, what is space made of that could carry such a thing? If space was truly empty, how could it support wave-like behavior as a basic fact of nature? This is the point where modern physics begins to shift its footing. The answer that slowly assembled over decades, through the work of many minds, was not that particles are little objects drifting through emptiness. The answer was that emptiness is not empty, not because it's filled with dust or hidden matter in the everyday sense, but because it is permeated by something deeper, fields. In the older familiar world, we already know fields exist. A magnetic field can fill a region of space. An electric field can exist around a charged object. A gravitational field can describe the influence of mass. But the quantum idea goes further. It suggests that fields are not just something that sits on top of reality. Fields are the foundation. They are not the scenery. They are the stage itself. It's a difficult shift if you try to force it all at once, so let it arrive slowly. Imagine the universe not as empty distance with objects sprinkled inside, but as a continuous presence, a kind of underlying structure that is everywhere, not a solid substance you could scoop into a cup, but a set of values at every point, an invisible something that can be calm in one moment and vibrate in another. Now imagine that what we call a particle is not a tiny object traveling through space like a pebble thrown across a room. Instead, a particle is a localized vibration in that underlying presence, a disturbance, a brief concentrated pattern, like a ripple on a surface that was otherwise still. When the ripple is there, you can point to it, you can track it, you can measure it. It looks like a thing, but it is never separate from the medium that carries it. The wave is not an extra object added to the ocean. It is the ocean, temporarily taking on a shape. This is the gentle, unsettling heart of the modern view. The universe may not be made of tiny bits of stuff moving through nothing. It may be made of fields, continuous layers that exist everywhere, and what we call stuff is simply the way those fields appear when they vibrate. Even if you don't follow every detail, you can feel the emotional weight of the idea, because it changes what you think you are. If matter is vibrations in deeper fields, then your body is not a collection of little beads of substance packed together in a void. Your body is a stable pattern, a persistent arrangement of excitations held in place by rules of interaction. And the space around you is not a blank gap separating you from the world. It is the same underlying fabric in a quieter mood. So, when you look at the darkness between stars, you are not looking at nothing. You are looking at something so subtle that the human senses evolved to ignore it. And that makes sense. Fish don't feel wet as a constant alarm, because water is the medium they've always lived in. A swimmer doesn't feel the pressure of the ocean as a moment-by-moment surprise, because the body adapts. In the same way, we don't feel the fabric of space-time or the omnipresent background of fields because we have never been outside them. They're not an environment we step into. They are the condition of our existence. If Einstein taught us that space can curve and respond, then quantum physics asks us to take the next step. Space is not merely a responsive fabric. It is filled everywhere with the potential for vibration, pattern, and form. The emptiness is not emptiness. It is the quietest arrangement of reality, a calm baseline, still capable of supporting waves, still capable of becoming matter, still capable of holding a universe together. And that may be the most soothing thought of all if you allow it to soften inside you, because it means you are not a small, isolated object drifting through blank darkness. You are part of a continuous structure, connected, supported, and held by something that does not begin at the edge of your skin and does not end at the edge of your room. Even in the most distant, silent region between galaxies, the foundation remains. Even here, in your quiet space, the foundation remains. And as you rest tonight, you can let that idea become less like a concept and more like a feeling. Not a thought you have to solve, just a gentle reminder that beneath everything you worry about, beneath the noise of the day, there is a deeper layer that is always present, a fabric that can bend, a medium that can carry waves, a reality that is not empty, even when it looks like it is. And with that, the old picture of space as a blank stage begins to fade, replaced by something stranger and more alive, something that is not merely where the universe happens, but part of what the universe is. For a long time, the human mind wanted reality to be built from objects, little pieces of something, tiny units you could imagine stacking like bricks, until the whole universe was assembled from solid, countable parts. It's an old instinct. It feels practical. If you zoom in far enough, surely you find the building blocks. And once you find them, you feel like you've reached the bottom of the story. But modern physics gently asks you to loosen your grip on that instinct. Because the deeper we look, the more reality stops behaving like a collection of things and starts behaving like a set of patterns, not objects moving through emptiness, patterns moving through presence. Here is the quiet shift that changes everything. A quantum field is not something that exists only where a particle happens to be. A quantum field is something that exists everywhere, at every point in space, and at every moment in time. It's like an invisible layer woven into the fabric of the universe, with a value at every location, the way temperature has a value at every point in a room. You might not feel it, but it's still there. And when that field changes, when it vibrates, oscillates, ripples, those ripples are what we call particles. This is one of the most profound reorganizations of reality ever discovered, because it means particles are not fundamental things. They are events. They are disturbances. They are brief, localized expressions of something deeper. If you want a calm image to hold on to, imagine an ocean stretching in every direction. Not an ocean of water, but an ocean of possibility. When the surface is perfectly calm, you don't point to a specific wave and say, "There it is." There's no crest, no motion you can isolate, but the ocean still exists, quietly, continuously, holding its potential. Now imagine a small wave rising, a gentle crest. Suddenly you can point to something, you can track it, you can say, "There is a wave," but the wave is not separate from the ocean. It is the ocean, temporarily taking on a shape. That is the core intuition behind quantum field theory. The electron is not a tiny bead traveling through empty space. The electron is a ripple in the electron field. A photon is not a little bullet of light flying like a microscopic projectile. A photon is a ripple in the electromagnetic field. Turn off a flashlight and the photons vanish. The light is gone, but the field remains, waiting, calm again, but still present, still capable of becoming light the moment it's disturbed. And once you let yourself think this way, the world around you begins to look strangely different. The chair beneath you, the air around you, the screen in front of you, your own body. All of it can be reimagined as a layered symphony of fields, overlapping and interacting, each one a continuous presence, each one capable of vibrating into the particles we observe. It's almost poetic, but it's not poetry. It's the most precise framework physics has ever built, predicting the behavior of matter and energy with astonishing accuracy. And it comes with a strange kind of comfort, because it suggests that emptiness is never truly empty. Even in the dark gaps between galaxies, regions where no atoms drift for millions of light years, the fields are still there. Quiet, yes, but not absent. There is still an electron field passing through that void, still an electromagnetic field, still other fields layered together like invisible atmospheres. In the standard model of particle physics, the picture becomes even more concrete. For every type of fundamental particle, there is a corresponding field. The electron field gives rise to electrons. Quark fields give rise to quarks. The gluon field gives rise to gluons. The electromagnetic field gives rise to photons. There are on the order of a few dozen such ingredients in total, often summarized as roughly 17 fundamental fields, depending on how you count them. It's a modest number, not infinite, not chaotic, a small set of foundational layers, and from their vibrations, the entire visible universe emerges. If you could somehow see these fields, you wouldn't see separate, isolated things. You'd see continuous oceans stacked on oceans, permeating one another everywhere at once. And in regions where these oceans are disturbed, where the vibrations become concentrated, you would see what we call matter. A proton, for instance, is not a single object. It's a structured pattern of excitations in quark fields, held tightly together by excitations of the gluon field. An atom is not a tiny solar system of objects. It's a stable choreography, fields interacting in a way that produces the enduring illusion of solidity. And you are not the exception. This is where the idea becomes intimate, because if the fields are everywhere, then they are here too, right now, passing through you. Not because you're special, but because you are made of the same underlying reality as everything else. The electron field doesn't stop at the boundary of your skin. The electromagnetic field doesn't pause politely outside your body. These fields are not localized substances. They do not begin and end the way everyday objects do. They are omnipresent. They don't visit you. They are the condition that makes you possible. So, when you imagine yourself as a person lying in a room, try, just for a moment, to let that picture soften into something deeper. Picture the fields as vast and continuous, and picture your body as a region where many of them overlap and vibrate in a remarkably organized way. A temporary convergence, a stable pattern, a kind of standing wave, held together by the rules of interaction, lasting long enough to breathe, to think, to wonder, to dream. This is why quantum fields are sometimes described as the universe's operating system. They are the underlying code running beneath the visible interface. What you experience is the interface: chairs, walls, stars, hands, heartbeat. But underneath, beneath what the senses evolved to notice, is a deeper layer that is quietly executing the same rules everywhere. It also changes what separation means. If matter is a disturbance in continuous fields, then the boundaries we obsess over, between self and world, between object and background, are not as fundamental as they feel. They are patterns of concentration, regions where vibrations cluster more densely. The difference between you and not you becomes less like a hard wall, and more like a gradient, a gentle shift in where the ripples are strongest. That doesn't erase individuality in any practical sense. You still have a name, you still have a history, you still have a life. But it suggests something quietly beautiful. At the deepest level, you are not made of separate stuff floating in a void. You are made of the same continuous reality that fills the universe. You are not an object thrown into space. You are a pattern that space itself can take. And if that sounds abstract, you don't have to strain to get it. You can let it be a feeling rather than a puzzle. The fields are always here, calm beneath the surface of appearances, sometimes vibrating into light, into matter, into the warmth of a living body. sometimes settling back into quiet. And whether you are awake and thinking, or drifting towards sleep, that deeper layer does not change. It remains steady in its presence, holding every moment the way an ocean holds every wave. So if your mind wants something simple to rest on tonight, let it be this. Reality is not built from isolated things. Reality is built from fields, everywhere, always. And you are one of the ways those fields have learned to take shape. And in the softness of that idea, there is a gentle question waiting. The kind that naturally rises when you begin to see the universe as layers of invisible oceans. If fields give rise to particles, and particles make up matter, then what gives matter its heaviness? What gives a ripple weight? What makes a pattern feel like mass? There is a simple question that sounds almost too ordinary to be profound. Why do things have mass? Why does a mug feel heavy in your hand, while a beam of light, no matter how intense, can cross the universe without ever slowing down? For a long time, the question barely felt like a question at all. Things were heavy because they were made of matter. Matter was heavy because that's what matter does. And if you trace the chain far enough, mugs to atoms, atoms to electrons and protons, the story often ended in a shrug. They have mass because they have mass. But in physics, because it is never the end of the road. It's a sign that a deeper layer is waiting. In the middle of the 20th century, as scientists began assembling what we now call the Standard Model, the framework that describes fundamental particles and forces, they discovered something unsettling. The equations, as elegant as they were, didn't want mass to exist, not in the way the universe clearly displays it. In the pure, symmetrical form of the theory, particles like electrons and quarks should behave as if they were weightless, and the carriers of the weak nuclear force, the W and Z bosons, should move like light itself, never slowing, never clumping into the stable structures that make chemistry possible. Yet, here we are, standing on floors, sitting in chairs, living in bodies that have weight. So, something was missing from the picture. And the missing ingredient wasn't a new particle in the usual sense. It was something more subtle and more pervasive, a field, an invisible ocean that fills all of space. In 1964, several physicists independently proposed a solution, and one name became most closely associated with it: Peter Higgs. What they suggested was that space is not an empty background where particles merely travel. Space is saturated with a field, now called the Higgs field, that never turns off. It is present everywhere. In the deep darkness between galaxies, the Higgs field is there. Inside the atoms of your body, it is there. In this very room, in the air you aren't thinking about, it is there. And it does something quietly dramatic. It makes certain particles behave as if they have mass. To sense what that means, imagine walking across an empty room. You move freely. There's nothing to slow you down. Now imagine the same room filled, not with air, but with thick water. Or, thicker still, something like syrup. Suddenly, movement feels different. It's not that you gained extra stuff attached to your body. Your body didn't become larger or more solid in a visible way. But the interaction between you and the medium changed the experience of motion. You feel resisted. You feel slowed. You feel heavier. That's the basic intuition behind the Higgs field. Certain particles interact with it strongly, and that interaction creates what we interpret as mass. It's as if the universe is filled with an invisible substance, not a substance you could bottle, but a property of space itself. That makes some particles sticky as they move. The stickier the interaction, the heavier the particle. The gentler the interaction, the lighter it behaves. And some particles don't interact at all. That last point matters because it explains one of the clearest differences in nature: why light is weightless. Photons, ripples in the electromagnetic field, do not couple to the Higgs field. They slip through this invisible ocean without resistance. Nothing grabs them, nothing slows them. So, they travel at the cosmic speed limit forever, crossing billions of light years with the same effortless pace. Electrons, on the other hand, do interact, though not as strongly as some heavier particles. So they carry a modest mass. Quarks interact too, and some of them, like the top quark, interact so strongly that they become astonishingly heavy. In the language of physics, the stickiness is captured by something called a coupling. But you don't need to hold that word tightly. What matters is the feeling of it. The universe assigns different degrees of resistance to different patterns in its fields, and that resistance shapes the world we live in. For decades, the Higgs field was a brilliant idea that fit beautifully into the theory, but remained unconfirmed. Physicists could write the equations, predict the consequences, and build the standard model into a remarkably accurate machine. But science is not satisfied by elegance alone. It wants evidence. If the Higgs field is real, then it should have a telltale signature, a particle associated with it, an excitation in the Higgs field itself, a ripple in that ocean, something that could, in principle, be created in sufficiently energetic collisions. The trouble was that producing such a ripple requires enormous energy, far beyond what any ordinary laboratory can provide. You need a machine that can fling particles at nearly the speed of light and smash them together like microscopic thunder. That machine exists. It's the Large Hadron Collider at CERN. And on July 4th, 2012, after years of work and oceans of data, scientists announced what sounded like a quiet miracle. They had found a new particle consistent with the Higgs boson. The field was no longer just a beautiful idea. It had left fingerprints. A year later, in 2013, the Nobel Prize in Physics was awarded to Peter Higgs and François Englert for the theory that explained how particles acquire mass. In the public imagination, the Higgs boson gained an infamous nickname, the God particle. Higgs himself disliked it, and for good reason. The name suggests mysticism, but the real wonder is not mystical at all. It's physical, concrete, almost tender. Because without the Higgs field, the universe would be unrecognizable. If electrons and quarks were massless, they would race at light speed. Atoms would not form the way they do. Chemistry, the intricate dance that allows molecules to exist, would not unfold into the rich complexity we call life. Stars, planets, bodies, breath. The stable structures we take for granted would dissolve into a blur of radiation and chaos. The Higgs field is one of the quiet conditions that makes stuff possible. Yet there is an even stranger twist, one that feels like a secret hidden inside your own weight. When you step on a scale, most of what you call your mass does not come directly from the Higgs field. That might sound impossible, but it's true. The Higgs field gives mass to fundamental particles like electrons and quarks, but protons and neutrons, the building blocks of atomic nuclei, are not fundamental. They are composite structures, three quarks bound together by the strong force, mediated by gluons. The quarks inside a proton do get their individual masses from the Higgs field, but that accounts for only a tiny fraction of the proton's total mass, roughly around 1%. So, where does the rest come from? From energy. From the intense binding energy trapped inside the proton, energy stored in the gluon field, and the motion of quarks confined in a tiny region. In Einstein's language, energy and mass are two faces of the same thing. E equals mc squared. That means energy contributes to mass. So, when you feel your body's weight, you are feeling not just matter, but energy held in a stable pattern, fields interacting, vibrating, and confining one another into something that can endure. This is one of the most beautiful rearrangements of perspective in physics. You are not a pile of solid substance. You are a structured pattern of field activity, stabilized by forces and filled with energy that behaves as mass. And the Higgs field is the quiet ocean that allows the first step of that pattern, the existence of massive particles, to be possible at all. There is also a cosmic story here, one that reaches back to the earliest moments of the universe. In the first fraction of a second after the Big Bang, the universe was unimaginably hot, so hot that the Higgs field did not behave as it does now. In a sense, the ocean had not yet settled into its present calm state. Particles moved differently. Mass did not exist in the familiar way. But as the universe expanded, it cooled. And at a critical threshold, something like a phase transition occurred, like water freezing into ice, or steam condensing into liquid. The Higgs field switched on, taking on a non-zero value everywhere. Suddenly, particles began to interact with it in a stable way. Mass became part of the universe's grammar. From that moment onward, atoms could form, stars could ignite, galaxies could gather, and eventually, in one small corner, life could emerge. Complex patterns of field activity that could look up at the cosmos and ask how they came to be. So, as you rest tonight, you can hold a gentle image in your mind. Not the image of empty space surrounding you, but the image of space filled with a calm, invisible presence. An ocean you never see, yet one that gives you weight. One that makes your body substantial. One that allows matter to move slowly enough to hold together, to build, to become. You are moving through that ocean now, in every moment of your life. And even as your thoughts soften, even as your breathing becomes slower and your awareness grows quieter, the Higgs field remains steady and everywhere, giving form to the particles that make you possible. And beneath that steady ocean, there is another kind of motion, more restless, more unavoidable. Because even when a field is in its lowest state, it is never perfectly still. In everyday life, the lowest energy state of something feels like stillness. A pendulum that is finished swinging hangs quietly. A ball rolls to a stop. A stretched spring settles into equilibrium. If you could cool a system down far enough, down toward absolute zero, it feels natural to imagine that every last bit of motion would fade away, leaving behind perfect calm. Classical physics encourages that picture. It suggests that the ground floor of reality is silence. But quantum physics does something strange to that comforting idea. It says you can never reach perfect stillness. Not because your instruments are imperfect, and not because you failed to remove all disturbances, but because reality itself will not allow it. At the smallest scales, nature has a built-in restlessness, an irreducible, unavoidable jitter that remains even when everything should, by intuition, be quiet. That restlessness is tied to one of the most famous ideas in all of physics, Heisenberg's uncertainty principle. You may have heard it described as a limit on knowledge. You can't know a particle's exact position and exact momentum at the same time. The more precisely you pin one down, the more the other becomes fuzzy. But the deeper message is not about human ignorance. It's about how reality behaves. It says the universe does not permit a perfect frozen state in which everything is exactly defined and perfectly still. If a quantum system could be completely motionless, exactly fixed in place with exactly zero momentum, the uncertainty principle would be violated. So nature pays for certainty with motion. Even in the lowest energy state, there must be fluctuations, a background hum, a gentle, ceaseless trembling in the fields that fill space. This is what physicists call zero-point energy. The minimum energy that remains when a system is as quiet as it can possibly be. It is not heat. It is not the kind of vibration that comes from warmth or friction. It does not fade away when you remove every last source of thermal agitation. It is something deeper, the residual movement of quantum fields themselves. And once you begin thinking in terms of fields, the idea becomes almost inevitable. If fields are the foundation, if they exist everywhere, then the vacuum is not an absence of fields. It is simply a state where those fields are not excited into real, detectable particles. The waves are not rising into crests you can point to. But the ocean is still there, and quantum mechanics says the ocean cannot be perfectly smooth. There is always a ripple, a shimmer, a seething possibility that never quite disappears. This is where the phrase, empty space is full of energy, stops sounding like a paradox and starts sounding like a statement of fact. Even the emptiest region of the universe, the darkest void between galaxies, still contains quantum fields. And those fields, even at their baseline, carry energy. They fluctuate, they jitter, they hum with potential. One of the strangest ways to talk about these fluctuations is through the idea of borrowing energy. Quantum mechanics includes a version of uncertainty that links energy and time. It suggests that, for a very short time, the energy of a system can fluctuate by a small amount, without violating the deeper rules, so long as the fluctuation doesn't last. The shorter the time window, the larger the fluctuation that can occur. It's not a loophole in the laws of nature. It's part of how the laws are written. And in the vacuum, inside this quiet baseline hum, those energy fluctuations can briefly take shape as particle-like events. An electron and its antimatter partner, a positron, might appear for an instant and then vanish. A flicker, a ghostly crest on the ocean that rises and falls before you can grasp it. These are often called virtual particles. You can think of them as the vacuum's brief daydreams, momentary excitations that never become fully real in the sense of reaching a detector as a stable particle, yet still leave measurable traces on the world. But even before you think about virtual particles, it's worth holding the simplest part of the idea in your mind. The vacuum is not calm. It is the quietest form of motion. And this isn't just philosophy or poetic language. The vacuum's restlessness shows up in experiments. One of the most famous early hints came from something that seems almost delicate, a tiny shift in the energy levels of hydrogen. In the classical picture, hydrogen's electrons should have energy states that match a clean mathematical pattern, and for the most part, it does. But in the real world, the energy levels are slightly off by a minuscule amount. In the 1940s, physicists predicted that the vacuum itself could be responsible. The electron in a hydrogen atom is not floating in a silent nothing. It is embedded in the fluctuating electromagnetic field. Even when there are no real photons present, the field still jitters, and that jitter subtly nudges the electron's energy. In 1947, Willis Lamb measured this effect with exquisite precision. The shift was tiny, less than a part in a million, but it was there. A small, undeniable message. The vacuum is alive with activity. Empty space is not an inert background. It participates. In that sense, zero-point energy is a kind of quiet proof that nothingness is not the opposite of something. Nothingness is simply the lowest mode of something, fields in their most subdued state, still unable to be perfectly still. And once you accept that, your picture of the universe changes again. Because now space isn't just geometry. It isn't just a curved fabric, as Einstein taught us. It's also a reservoir of quantum motion, a restless baseline that exists everywhere, all the time. So why don't we notice it? In a way we do. We just don't recognize it as the vacuum. The stability of atoms, the precise values of physical constants, subtle shifts in energy levels, these are not side details. They are part of the structure that makes the world behave the way it does. We're immersed in the vacuum the way fish are immersed in water pressure. The background is so constant that the senses treat it as normal and move on. But experiments and theory keep tugging us back to the same realization. The vacuum has properties. The vacuum has energy. The vacuum exerts influence. And then there is the most haunting implication of all. When physicists try to calculate how much zero-point energy should exist, the number becomes absurdly large. If you take the quantum fields and add up the energy of all their possible modes across all frequencies, you get a vacuum energy density so enormous it barely fits inside language. So enormous that, if it were literally present in the way naive calculations suggest, the universe would not look anything like the one we see. Space would curve violently. Expansion would be catastrophic. Reality would be unrecognizable. Yet the universe is not exploding with that energy. The sky is calm. Galaxies form and persist. So something is missing from our understanding. Either the calculation is incomplete, or some mysterious cancellation occurs, or the vacuum energy behaves differently when gravity enters the story. This mismatch is known as the cosmological constant problem, and it remains one of the deepest puzzles in physics. It's the universe quietly telling us that we understand enough to see the shape of the mystery, but not enough to solve it. And that mystery is both unsettling and strangely soothing. Unsettling because it reminds us that even our best theories still have blind spots. Soothing because it suggests the vacuum is not hostile chaos. It's a structured restlessness, a governed hum that has held the universe together for billions of years. So, as you rest tonight, you can let that image become gentle in your mind. Imagine the space around you not as blank emptiness, but as a soft, invisible sea. Not stormy, not loud, just quietly alive. A field that cannot fall perfectly silent. A baseline vibration that never truly stops. And out of that hush, out of that constant subtle trembling, come fleeting, almost ghost-like events. Brief patterns that shape forces and matter, even though they never settle long enough to be held. In the vacuum, nothing is ever completely alone. Even nothing has a kind of traffic. If the vacuum is never truly still, if it carries that constant, irreducible hum, then it becomes natural to wonder what that hum is actually doing. Not in a dramatic fireworks kind of way. More like the way a quiet room is never perfectly silent. Even when you sit very still, there is always a faint presence in the background, the smallest vibrations in the air, the soft shift of temperature, the subtle movement you didn't notice until you paid attention. In the quantum world, that background presence can briefly take shape. For a moment, the vacuum can behave as if something has appeared inside it, an echo of a particle, a flicker of activity that rises and falls too quickly to be held. These fleeting events are what physicists call virtual particles. The name can be misleading because it sounds like they are imaginary. But virtual here doesn't mean made up. It means they are not directly observable as free, stable particles the way a photon in a detector is observable. They are internal, temporary processes, short-lived excitations in a field, allowed by the strange rules that govern energy and time. There is a version of the uncertainty principle that whispers a remarkable possibility. For a very short time, energy can fluctuate, not because the universe forgets conservation, but because quantum mechanics allows a kind of blur over extremely small time windows. The shorter the time, the larger the fluctuation can be. It's not a loophole you can exploit to get something for nothing. It's more like a natural vibration, an unavoidable wobble in the bookkeeping of reality, so brief that the overall balance remains intact. And in that brief wobble, the vacuum can borrow enough energy to produce a particle-like disturbance. An electron and a positron might appear together, matter and antimatter, like a pair of ripples rising from a calm surface. Almost immediately, the pair vanishes, collapsing back into the quiet baseline of the field, as if the ocean never changed at all. This is one of the most challenging things to let into your intuition. That empty space can host events, even when no real particles are present. But once you begin thinking in terms of fields, it becomes less like magic and more like weather. A field is an ever-present medium. If it cannot be perfectly still, then it will fluctuate. And if it fluctuates, then it will occasionally form brief, localized patterns. Tiny, momentary, almost particles that shape how real particles behave. That last part is the key. Virtual particles are not just oddities. They are not just philosophical decoration. They matter because they help explain how forces work. In our everyday intuition, forces feel direct. Two magnets attract, two charges repel, gravity pulls. One object tugs on another across what looks like empty space, and we accept it because we're used to it. But quantum field theory tells a different story. It suggests that interactions are mediated. Forces are not simply reaching across the void. They are carried by exchanges, tiny transactions in the fields that fill space. And the carriers of those exchanges, in many cases, are virtual particles. One of the most elegant ways physicists visualize this comes from Richard Feynman, who introduced a kind of pictorial language for interactions. Feynman diagrams. They look simple, lines that meet, split, and reconnect. But inside that simplicity is a profound shift in how we imagine reality. When two electrons repel, they don't push each other directly like billiard balls. In the quantum story, they exchange a photon, the particle associated with the electromagnetic field. But in this case, the photon is not a free, real photon you could catch. It's a virtual photon, a brief excitation that exists only in the interaction itself. One electron emits it, the other absorbs it. Momentum is transferred, the repulsion emerges. And that kind of exchange is happening constantly, everywhere, all the time. Not as a dramatic event you could point to, but as a quiet, ongoing traffic in the fields. A ghost traffic that makes the world behave the way it does. The same pattern holds for the other forces. The strong nuclear force, the force that binds quarks into protons and neutrons, is mediated by gluons, and those gluons can appear virtually in the interactions that keep nuclei stable. The weak force, the one responsible for certain kinds of radioactive decay, is mediated by W and Z bosons, often appearing in virtual form during processes that change one particle into another. And if gravity has a quantum description, it would likely involve a carrier as well, often called the graviton, still hypothetical, still undetected, but conceptually fitting into the same framework. So in a quantum universe, no particle is ever truly alone. Every electron is surrounded by the possibility of exchange, embedded in a fluctuating field that is always active, always willing, at least briefly, to take on a particle-like form. This leads to one of the most subtle consequences of virtual particles. They don't just mediate forces between particles, they can also dress the particles themselves. In the cleanest, simplest picture, an electron is just an electron, one neat excitation in the electron field, but the real quantum world is messier, richer, and more alive. An electron is surrounded by a cloud of virtual activity, virtual photons being emitted and reabsorbed. And those virtual photons can themselves briefly fluctuate into virtual electron-positron pairs, and so on. The electron becomes a kind of center of influence in the field, wrapped in a shimmering halo of virtual processes. And that halo changes what we measure. At a distance, the electron's charge appears slightly different than it would if you could somehow strip away the cloud and see the bare excitation beneath. The vacuum, through its constant fluctuations, partially screens the charge, the way fog can soften a light. You don't need the technical machinery of renormalization to feel the intuition. What you measure is not just a particle, but a particle plus the vacuum's restless participation around it. Even mass is touched by this. Because energy contributes to mass, the energy of those virtual processes becomes part of the effective mass you observe. When physicists measure the properties of particles with extreme precision, they are measuring the particle and the vacuum's contribution, woven together into a single behavior. And again, this isn't merely a story, it shows up in measurements. The Lamb shift you heard about a moment ago is one example. The energy levels of hydrogen are nudged because the electron is interacting with vacuum fluctuations and virtual photons. Another famous confirmation comes from an exquisite number, the electron's magnetic moment. The electron behaves like a tiny magnet. Quantum electrodynamics, the quantum theory of electromagnetic interactions, predicts the strength of that magnetism with astonishing precision. But the prediction only matches experiments when you include the effects of virtual particles, when you account for that surrounding cloud of quantum activity. It's one of those moments where the universe seems to say, gently and firmly, yes, the vacuum is doing something, and you can measure it. So are virtual particles real? It depends on what you mean by real. If real means something you can isolate, trap, and observe directly as an independent object, then virtual particles are not real in that way. They are too fleeting. They appear inside interactions and vanish before you could ever point a detector at them. But if real means they produce measurable consequences, if they alter energy levels, shift magnetic moments, and mediate the forces that hold atoms together, then their reality is hard to deny. They are processes that leave fingerprints. They are the vacuum's influence made tangible through effects. Sometimes it helps to loosen the grip of the word particle altogether. Think of virtual particles not as little beads popping into and out of existence, but as brief field behaviors, temporary patterns that act particle-like in the mathematics and in the way they shape interactions, without being standalone objects. And if you want a more playful image, one that still carries the truth, Imagine the vacuum like a cosmic jukebox. A jukebox doesn't contain a single song playing forever. It contains the potential for songs. Most of the time, it's quiet. But now and then, something triggers a brief burst, a few notes, a short melody, a fragment of sound that appears and then stops. The quantum vacuum is like that, except the songs are fleeting excitations, virtual photons, virtual electron pairs, virtual whispers of the fields that make up the universe. The jukebox is never fully unplugged. It's always humming with the possibility of playing something for an instant and then falling quiet again. That's the vacuum's nature, not dead emptiness, but living potential. And in that living potential, the forces of nature are carried, shaped, and continuously renewed. Now here's where the story becomes almost touchable. Because if the vacuum is filled with fluctuating modes, if there is a constant sea of allowed vibrations, then changing the shape of space can change what the vacuum can do. Limit which modes can exist in a region, and you create an imbalance, a pressure difference, a push. There is a phenomenon where nothing doesn't just influence particles indirectly, but presses on matter in a way we can measure with careful instruments. A place where the vacuum, in a sense, answers back. And all it takes is bringing two uncharged surfaces very close together and letting the ghost traffic of the quantum ocean reveal its weight. Imagine two pieces of metal, clean and uncharged, suspended in a near-perfect vacuum. No batteries, no magnets, no static cling. Nothing about them should feel dramatic. In a classical picture of the universe, they ought to sit there quietly, like two calm stones on a table, indifferent to one another. And yet, if you bring those surfaces close enough, close in the way only careful instruments can manage, they begin to move. Not because of gravity in any meaningful way, not because of hidden electric charge, not because one plate is secretly pulling on the other like a tiny magnet. They move because empty space has rules. Because the vacuum is not a blank absence, but a restless background filled with possible vibrations. And when you place boundaries inside that background, two surfaces facing each other, you change which vibrations are allowed to exist between them. This is the Casimir effect. It's one of the most intimate ways the universe has of telling us, softly and unmistakably, that nothing is not nothing. To feel the logic of it, it helps to think about waves, not ocean waves this time, but the kind of waves that can exist in a field. The electromagnetic field, for example, can vibrate at many wavelengths. In an open region of space, those wavelengths are free to take on almost any value. The vacuum can hum with an enormous range of modes, some long, some short, some subtle, some intense, like a choir warming up where every singer is allowed to choose a note. But between two closely spaced surfaces, that freedom is restricted. It becomes more like a musical instrument. A guitar string cannot vibrate at just any frequency. Only certain patterns fit neatly along the string, patterns where the ends remain fixed. If the string is shorter, fewer low notes fit. If the string is longer, deeper notes become possible. Now translate that intuition into the space between two plates. When the plates are far apart, many wavelengths can fit between them. But when the gap becomes very small, the longer wavelengths simply can't fit in the space. The vacuum between the plates is forced into a narrower selection of allowed modes. Outside the plates, the vacuum has no such restriction. It can host the full range of fluctuations. So, you end up with an imbalance. More possible vacuum modes outside the plates than inside. And that imbalance behaves like a pressure difference. It's not a pressure you can feel with your skin, the way you feel air pushing on you. It's a quantum pressure, a tiny net push that comes from the fact that the vacuum's fluctuations are unevenly distributed when boundaries are introduced. The outside has a richer spectrum of vacuum activity, the inside has less, and the plates are gently pressed together. If that sounds almost too delicate to be real, it helps to remember how often nature works through differences. A breeze is a pressure difference. A current is a difference in electric potential. A flow of heat is a difference in temperature. The Casimir effect is another one of those quiet, universal habits. When conditions aren't balanced, something moves. What makes the Casimir effect so haunting is how clean it is. There's no need to assume hidden charges or mysterious forces. The effect emerges from the structure of the vacuum itself, like a shadow that appears not because someone painted it, but because you placed an object in the light. When Dutch physicist Hendrik Casimir proposed this in 1948, it sounded like a beautiful piece of theory, elegant, strange, and hard to test. The force involved is extraordinarily small. You're working with separations on the scale of micrometers and forces that can be comparable to the weight of something like a tiny grain of dust spread over an area. For decades, it lived in that place where quantum ideas sometimes linger, convincing on paper, elusive in practice. Then, in the late 1990s, a set of experiments brought the vacuum's whisper into the measurable world. One of the most famous was performed by Steve Lamoureux at the University of Washington in 1997. The setup was both simple in concept and astonishing in execution. Instead of trying to keep two perfectly parallel plates aligned, which is maddeningly difficult at microscopic separations, Lamoureux used a sphere and a plate coated with gold. The geometry made the measurement more practical, while still preserving the essential physics of a tiny gap. To detect the force, he used a torsion pendulum, a delicate device that can sense minuscule pushes and pulls by measuring a small twist in a suspended system. It's the kind of instrument that feels almost poetic, something that turns invisible pressure into visible motion. As the gold-coated sphere approached the gold-coated plate, the torsion pendulum registered a tiny attraction, matching the predictions of quantum field theory within a few percent. Not perfect at first, nothing about real experiments is ever perfectly clean, but close enough to confirm the core claim. The vacuum was not passive. The vacuum could push. And after that, the Casimir effect stopped being a curiosity. It became a phenomenon that engineers and physicists had to take seriously, not only in fundamental physics, but in technology. Because when you build devices that are extremely small, micro-electromechanical systems, nanomachines, tiny sensors, miniature components, the Casimir force stops being negligible. At those scales, forces we ignore in everyday life become dominant. Components can stick together. Moving parts can cling when they're meant to glide. Engineers even have a word for the problem: stiction. A kind of stubborn sticking that isn't quite friction and isn't quite glue, just the reality that, at tiny separations, the vacuum itself contributes a force that can pull surfaces into contact and keep them there. So, the Casimir effect is not just a late-night philosophical wonder. It's a practical feature of the modern world. It shows up in the design of nanoscale devices the same way humidity shows up in the design of wooden instruments. It's part of the environment at that scale, something you must account for if you want your creation to behave reliably. And once an effect becomes practical, the human mind does what it always does. It asks a new question. If the vacuum can push, can we tune the push? Can we shape it, soften it, strengthen it, or even reverse it? This is where the story becomes even more intriguing, because it hints at something deeper than simply, the vacuum has energy. It hints that vacuum forces might be engineered, guided, not just endured. In 2024, researchers reported progress toward precisely that kind of control, using special materials and magnetic fields. One approach involved ferrofluids, liquids filled with magnetic nanoparticles, placed in the gap between surfaces. Under the influence of a magnetic field, the properties of the medium can be altered, changing how electromagnetic fluctuations behave in the space between the boundaries. And if the fluctuations change, the pressure difference can change. Depending on the configuration, the Casimir force can be tuned, made weaker, stronger, and in some circumstances, pushed toward repulsion rather than attraction. That last possibility is especially striking because it flips the original intuition on its head. Not only is nothing something, but nothing might be something you can shape. At the nanoscale, that kind of control isn't just academically satisfying. It could reduce stiction, improve the reliability of tiny moving parts, and help design more stable micro-devices and quantum technologies, places where the boundary between physics and engineering becomes thin, and the vacuum's behavior becomes part of the blueprint. But the Casimir effect also stirs a much larger curiosity, one that reaches far beyond laboratories and microchips. Because if the vacuum has energy, if it contains a background of fluctuations that can exert real forces, then it's natural to wonder whether that vacuum energy is related to the largest mystery in cosmology: dark energy. On paper, the connection seems almost irresistible. Dark energy behaves as if space itself has an energy density, an energy of the vacuum that drives the expansion of the universe. The Casimir effect seems to prove that vacuum energy is not just mathematics. It can press on matter. It can create measurable forces. It can, in a sense, make its presence known. And yet, when physicists try to connect these two stories quantitatively, they run straight into a wall. The vacuum energy you can infer from quantum field calculations, when you sum over the possible modes of all fields, comes out absurdly large, far, far larger than what the universe's acceleration seems to require. The mismatch is so enormous that it feels almost like the universe is teasing us, giving us a clear, measurable demonstration that vacuum energy is real, and then refusing to let that energy explain the cosmos in any straightforward way. This is the cosmological constant problem, and it remains one of the deepest unsolved puzzles in physics. Something cancels, something suppresses, something about our accounting is incomplete, or something about the relationship between quantum fields and gravity is missing from the picture. But even without solving that mystery, the Casimir effect leaves you with a calm, steady realization. The vacuum is not a void. It is an environment. It has structure. It has rules. It has a kind of quiet pressure that only reveals itself when you give it boundaries, when you gently constrain the infinite ocean of possible fluctuations and listen for the imbalance it creates. So, if you're lying there now, letting your thoughts slow down, you might imagine space not as a blank emptiness around your body, but as a soft, invisible medium that can push back when shaped in just the right way. And then, if you let your curiosity drift smaller, past atoms, past nuclei, past anything you could hold in your hands, you arrive at a question that feels almost inevitable. If the vacuum can press on metal plates, what happens when the plates are the boundaries of space-time itself? What happens when the fabric we call space stops behaving smooth and begins to tremble at scales so small they're nearly beyond meaning? There's a quiet way the universe invites you to go deeper. Once you've seen that nothing can press on metal plates, once you've felt how the vacuum can behave like a real environment, it's hard not to wonder what happens when you keep shrinking the scale. Not smaller in the everyday sense, like dust or cells or atoms. Smaller in the almost unthinkable sense, down to the place where the very idea of a smooth, continuous space may begin to blur. Because the space you picture in your mind, clear, empty, and perfectly calm, is something your intuition invented for survival. It's a useful picture for throwing a ball, walking across a room, or watching clouds drift over a highway. But physics has been quietly suggesting, for a long time now, that smoothness might be an illusion, a kind of calm surface that only exists when you stand far enough away. And deep beneath that surface, there may be a texture, a grain, a trembling, a foam. In the 1950s, the physicist John Wheeler gave this idea a name that still feels strangely vivid: quantum foam. It's the image of space-time itself, space and time together, not as a perfect silent stage, but as something that flickers with microscopic activity when you zoom in far enough. Not flickers of particles in space, flickers of space itself. To understand why anyone would even suspect something like this, it helps to notice a tension that modern physics hasn't fully resolved. On one side, you have general relativity, Einstein's theory of gravity. In that story, space-time is smooth and geometric, mass and energy bend it, and that bending becomes gravity. It's a world of curves, horizons, and elegant continuity. On the other side, you have quantum mechanics, where the world is grainy, probabilistic, and never perfectly still. Even the vacuum has fluctuations. Uncertainty isn't a flaw in measurement. It's a feature of reality. Both theories are spectacularly successful. And yet, when you try to bring them together at the deepest levels, they begin to argue. Relativity wants space-time to be smooth. Quantum physics keeps insisting that nothing can stay perfectly smooth forever. So, physicists ask a simple, unsettling question. If you take space-time and zoom in, and zoom in, and zoom in, does it remain a continuous fabric, or does it eventually become something else? That eventually has a name too. It's marked by a set of scales called the Planck scale, where our usual language of distance and time starts to feel like it's being stretched beyond its limits. The Planck length is often given as about 1.6 × 10⁻35 meters, a decimal point, followed by more zeros than the mind enjoys holding on to. The Planck time is around 10⁻43 seconds, a fraction of a second so small it feels more like a concept than a duration. These aren't arbitrary numbers. They emerge when you combine the constants that govern gravity, quantum mechanics, and relativity, as if nature is quietly telling you, here is the region where your current maps run out. And in that region, Wheeler imagined space-time behaving less like a smooth sheet, and more like the froth on the surface of a stormy sea. Not big rolling waves you can surf, something far finer. Foam made of temporary curvatures and pinches and bubbles, so fleeting that they appear and vanish before anything classical can form. In this picture, space-time is constantly trying on tiny shapes. A microscopic tunnel here, a little pinch of curvature there, a brief localized warping that might resemble a tiny black hole popping in and out of existence. Even the idea of a point becomes suspicious, because in a foamy space-time, a point may not be a clean location. It may be a blur of possibilities, like trying to touch the exact crest of a ripple in the dark. Now, it's important to say this gently and honestly. Quantum foam is not something we've photographed or directly measured the way we measure a planet or a heartbeat. It's a conceptual bridge, an attempt to describe what might happen when quantum uncertainty is applied to the geometry of space-time itself. But the reason it persists is that it feels like the kind of answer the universe has been giving us all along. Again and again, the deeper we look, the more the solid world becomes a pattern. Atoms become mostly empty space. Particles become excitations of fields. The vacuum becomes active. So, it wouldn't be surprising, almost in the way a story's next line feels inevitable, if space-time itself also turns out to have a deeper structure. And because we don't yet have a complete, agreed-upon theory of quantum gravity, there are several competing ideas about what that structure might be. Some physicists explore string theory, where the fundamental ingredients are tiny vibrating strings, and space-time can have extra dimensions curled up in ways we don't perceive directly. In that view, the foam might be smoothed out by the extended nature of strings, less like sharp points, more like gentle threads. Others work on loop quantum gravity, which suggests that space might be quantized, built from discrete units, like a weave made of loops. In that picture, the fabric isn't infinitely divisible. It has a smallest stitch. And then there are approaches like causal sets, where space-time is described as a network of events connected by cause and effect, more like a skeleton of relationships than a continuous background. These are very different visions. They don't yet merge into a single story. But they share a common instinct, that space-time, at its deepest level, may not be smooth. And that matters, because some of the most dramatic places in the universe are places where smoothness breaks down in our current equations. Think of a black hole, where classical relativity predicts a singularity, an infinite density, a point where the math explodes and meaning dissolves. Many physicists suspect that this singularity is not a real object in nature, but a sign that we're missing the quantum description. In some quantum gravity ideas, the collapse that would form a singularity is halted by quantum effects, replaced by something like a bounce, or a compressed state that never becomes infinitely small. Not because the universe is trying to be kind, But because infinity is often where a theory is quietly admitting, I don't know what happens next. And if you let that thought settle, it can actually be soothing. Because it means the universe may be more structured, more lawfully restrained than our scariest mental images suggest. Even in the most extreme conditions, there may be deeper rules holding everything together, rules we're still learning to name. If you're listening and feeling your thoughts soften a little, you can let this be one of those moments you don't have to solve. You can just rest in the wonder of it. Because what we're really doing is practicing a different relationship with the unknown. We're letting questions exist without turning them into stress. We're letting the universe be big and strange and still safe to think about. And once you start to see the cosmos as an ocean of fields and space-time itself as something that may shimmer with hidden texture, another curiosity drifts naturally into view. If reality is made of patterns, fields, fluctuations, and perhaps even foamy geometry, then the most intimate pattern of all becomes impossible to ignore. The one that feels like awareness. The one that, in the quiet, you call you. There's a moment in every deep science story where the mind wants to reach for something personal. Not because the equations demand it, but because once you begin to see the universe as an ocean of invisible fields, patterns layered through every inch of space, it becomes strangely difficult to avoid one particular question. If everything is a pattern, then what is the pattern that feels like you? It's a tender question, and it deserves a gentle tone. Because consciousness is not one of those topics where science has a neat ribbon to tie at the end. There are good maps and fascinating landmarks and whole forests still unexplored. So, tonight we'll treat this as an honest speculation, something to wonder about, not something to prove in a bedtime voice. Start with what we know in the simplest way. Your brain is not a silent object. It's an electrical storm, but a quiet one. Billions of tiny signals moving through networks of cells. Every thought, every memory, every drifting image that crosses your mind as you lie in bed is linked to electrical activity. And where there is electric activity, there are fields. In fact, your brain generates faint electromagnetic fields that can be measured outside your skull. That's what an EEG is listening for. Not thoughts directly, but the rhythmic echoes of coordinated activity. So one soft idea begins here. Perhaps consciousness isn't located in a single point, like a candle flame inside the head. Perhaps it's more like a pattern that exists across a living network, an organized weather system of signals. Not one neuron, not one switch, but coordination. Synchrone. A choir, not a solo. In mainstream neuroscience, this kind of language shows up often. Many researchers describe conscious experience as emerging from integration, how information is combined, compared, and bound together into a unified moment. The details are debated, but the theme repeats. It's not the parts alone, it's the way the parts move together. And if you already accept that matter itself may be described as field patterns, it's tempting to lean into the poetry of it. A mind could be a field-like pattern too, dynamic, changing, yet coherent enough to feel like one continuous self. From there, some people take a further step, and this is where the conversation becomes more speculative. They ask whether the brain might sometimes exploit quantum effects, whether certain biological structures could maintain a delicate kind of coherence, even briefly, and whether that could play any role in consciousness. One of the most famous proposals along those lines is the OR idea associated with Roger Penrose and Stuart Hameroff, suggesting that microscopic structures in neurons called microtubules could be involved in quantum processes related to awareness. It's an intriguing thought, and it's also important to say calmly and clearly that it remains controversial. Many neuroscientists and physicists are skeptical, and the brain is warm, wet, and noisy, conditions that tend to disrupt fragile quantum states very quickly. Still, the reason these ideas linger isn't because they're proven. It's because we keep finding that quantum mechanics has a quiet habit of showing up in places we once assumed it couldn't. There are hints of quantum behavior in certain biological systems, like the efficiency of energy transfer and photosynthesis, and some models of how birds may sense Earth's magnetic field, Those aren't about consciousness, but they do whisper a broader point. Nature sometimes uses subtle physics in unexpected ways. So the question becomes less dramatic and more gentle. Could the brain, in some limited way, be sensitive to deeper layers of reality than we currently understand? And then there's an even softer idea, one that lives on the border between science and philosophy. If fields fill the universe, if the vacuum itself is not emptiness, but a structured medium, could there be something like an informational landscape beneath matter? Something that systems like brains might interact with? Some people describe this with the metaphor of an antenna. Not that your brain is literally receiving radio stations from space, but that it might be tuning into patterns, selecting, amplifying, and stabilizing certain modes of activity that become your conscious experience. As metaphor, it can be soothing, because it frames you not as an isolated object trapped in a skull, but as a living pattern, coupled to the world, shaped by it, responding to it. But again, we should keep our feet on the ground while our imagination drifts. Most scientists would not claim there is a known field of consciousness out there, in the way there is an electron field or a photon field. There is no accepted measurement of such a thing. The safest, most honest stance is wonder without certainty. And wonder is enough. Because whether consciousness is entirely an emergent property of neural networks, or whether it involves deeper physics we haven't yet connected, one thing remains beautifully true. You are not a static thing. You are a process, a pattern that renews itself from moment to moment, held together by rhythm, memory, and gentle continuity. And that means sleep isn't a disappearance. It's a soft rebalancing, a loosening of the day's sharp edges as your internal patterns settle into quieter shapes. If you'd like, you can leave a comment tonight with a simple thought. Do you feel more like a thing or more like a pattern? I read those, and they help shape future journeys. And if this kind of calm science speculation is the sort of company you enjoy at night, a like and a quiet subscribe helps others find the quantum slumber too. Because in the end, whatever consciousness turns out to be, it's still one of the universe's most intimate mysteries. A little pocket of awareness, looking back at the cosmos, and for a while, feeling safe enough to rest. Out on the largest scales, the universe behaves in a way that still feels almost dreamlike. For most of the 20th century, many scientists expected gravity to slow the expansion down, like a ball tossed upward that gradually loses speed. But in the late 1990s, careful observations of very distant supernovae suggested something stranger. The expansion isn't slowing, it's speeding up, as if the cosmos has a quiet engine built into the emptiness itself. Today, the simplest way to describe that engine is a name that sounds calm, almost gentle: dark energy. If you picture the contents of the universe like ingredients in a cosmic recipe, only a small portion is the familiar stuff: atoms, stars, planets, and you. Roughly 5% is ordinary matter. About 27% behaves like unseen mass we call dark matter. And around 68% appears to be this smooth, persistent push that makes space stretch faster over time. Here's the eerie part. One natural suspect is the vacuum itself, the same quantum vacuum we've been talking about, restless and structured even when it looks empty. In Einstein's equations, you can add a term that acts like an energy of space, often called the cosmological constant. It fits the broad story remarkably well. And yet, when physicists try to calculate what that vacuum energy should be using quantum field theory, the number comes out wildly, absurdly larger than what the universe actually seems to have, off by something like 120 orders of magnitude. It's one of the deepest mismatches in all of science, like a whisper measured against a hurricane. And lately, there are hints, still tentative, still under debate, that dark energy may not be perfectly constant. Some newer surveys have raised the possibility that it could change slowly over cosmic time, like a gentle tide rather than a fixed background. If that's true, the fate of everything could depend on a detail hidden inside the vacuum. But for now, it's enough to hold the wonder softly, The emptiness between galaxies may be shaping the destiny of the cosmos, while you, here in bed, shape the destiny of your next few hours simply by letting yourself rest. Before we drift away, you can try something simple, something that usually feels solid enough to end the conversation. Press your fingertips gently against the wall, or the blanket, or the edge of your mattress. It feels firm, certain, like matter is a hard thing, packed tight and unmoving. But beneath that feeling is a quieter truth. What you're touching is mostly empty space, held in place by invisible fields, by the soft, stubborn repulsion of electromagnetic patterns that refuse to overlap. The wall is not a wall in the way your intuition imagines it. It's a choreography, a balance, a relationship. And you too are not a single fixed object. If you could take away all the emptiness inside atoms, if you could squeeze out the gaps the way you'd press air from a pillow, your entire body could shrink to something impossibly small. Not because you vanish, but because so much of you is spaciousness, structured and held. Tonight, you don't have to solve the universe. Just remember this gentle idea. You are a pattern in an ocean of fields, temporary, meaningful, and real. As sleep arrives, the pattern doesn't disappear. It simply softens, like a wave settling back into the sea. May your rest be deep, your dreams be quiet, and your night feel safely infinite.